Hi, everyone, and welcome to AstroNights Live. Once again, we have a fascinating presentation planned for you, and we're very excited that you chose to spend a little of your time with us tonight. Our presentation will be about 20 minutes in length, after which you'll be able to address a few of your questions. Those of you participating on Zoom can post a question via the Q&A window. Be sure to hold your question until the end, because it might just get answered during the presentation itself. If you're joining us via YouTube Live, you should know that Q&A is not available, so just sit back and enjoy. Whether you're joining us on Zoom or YouTube, we recommend taking a moment to locate the full screen mode in your app for the best AstroNight Live viewing experience. All of the websites and resources we'll be discussing during our program are available on our website. So don't worry about rushing to write them down. Just relax and enjoy the program. The links will be waiting for you whenever you're ready. You'll be invited to complete an online survey at the close of the program, and we hope you take a moment to share your thoughts with us. Your feedback helps us in the planning of future AstroNight Live events. And now I would like to introduce you to our presenter, Mary McDonald. Mary is the Planetarium Programs Manager at the FSU Planetarium, and I know she's anxious to get started. Mary?
Thank you very much, John, and welcome everyone to AstroNights. My name is Mary, and I'm going to be your guide today. So our program today is called The Colorful Stars of Summer, and I think it is going to be a very colorful presentation. As often, we like to start off with a question. So I really hope that those of you who are watching at home are, doesn't matter if you're by yourself, but if you're with a group of people, I hope you're talking to each other a little bit. We might ask a couple of questions, and we really want you all to ask each other these questions and start a discussion. So I'm going to put up the first question to get us all started. This is something I want you all to think about. There we go. And those of you who are on Zoom, I am actually going to share this question in the form of a poll that you can participate in. So those of you on Zoom should now be seeing a poll. The question is, what can we learn about stars by studying their light? And you can possibly choose more than one. Now, anyone who has joined us on a previous AstroNights might recognize this question. It has been asked before. But supposedly I made a mistake last time and I only let people choose one option on the poll. So it's a hint that it is going to be at least more than one. So everybody on Zoom should be entering their answers, but everybody should be talking about this with each other. So take another moment to do that. All right, and I'm going to end the polling for those of us on Zoom at the moment. So make sure you have entered your answers and hit submit. Okay, ready? And let's end the polling. All right, so this is the results, and I can share the results actually. These are the kind of results that you might expect to see, a very widespread. Most of the answers were chosen. Most people thought at least someone thought at least one of these was true for every choice. And technically, the answer is that you can learn all of these things about stars by studying their light. What color they are, what they're made of, how big they are, how far away they are, how old they are, whether they have planets. You can learn all of those things about stars just by studying their light, which is great because that's the only thing we can do at the moment. We cannot travel to a star to take a sample. We can only study its light. But there is so much information that you can learn about stars from their light. And the very first one on this list, what color they are, that's perhaps one of the easiest. And there are many stars in the night sky where you can actually tell what color they are without even any special equipment. All right, I'm going to close the poll. And I hope that you're all thinking about all of these different things about stars and how we might possibly learn them. If you have questions about any of these things, we can discuss it more at the end of the show. And just to head off some questions, I will say that it is possible to learn each one of these things about a star from its light, but it doesn't necessarily mean you can do it for every star or that it's easy. All right, I'm gonna now switch us over to our view of the lovely night sky. So you should now be looking at the sky as it will appear tonight at about 8:15 p.m. So 8:15, it is not dark at all yet. The sun is still out. You have a lovely view of the moon as well. But our program tonight is about stars. So I'm going to let some time pass, and we are going to try to look out for some stars. And I have to now remember to turn off my video. Let's stop the video. And I have taken us forward to 10 o'clock. So I know 10 o'clock is a little bit late, maybe for our youngest audience members, but unfortunately you do kind of have to stay up that late in order to see a dark sky. And if you want more information about that, it's because we just recently passed the summer solstice. And if you do want to learn more about that, we did an AstroNights special event last week about the solstice, which you can watch on YouTube. And don't forget, at the end of the program, I will be talking about how you can access lots of resources, including the old AstroNights. Okay, so you should be looking at a lovely dark night sky. If possible, those of you at home might want to try to get the room around you as dark as you can so that you can see a little bit more of the contrast with the stars. And remember, I said we're talking today about the colors of the stars. So looking at the stars, whether it is here on your screen or in the real night sky, most of the stars typically look white. But I would like you to look at this field of stars on your screen and ask each other, do you see any stars that appear a different color besides white? So have a look, everybody. All right. Now, first of all, no matter what you've just said to each other about the colors of the stars, what color they appear to you, no matter what you've said, you're not wrong. Because first of all, there are many stars in the sky that do appear different colors. And also, not all of us see colors exactly the same. So something that might look very vibrant to you might look less vibrant to another. But did anybody at home take a look at this star right here? Was this one that jumped out at anyone as being an interesting color? Well, if so, you are not alone, because this is a star that to many people is quite obviously a reddish color. The name of this star is Antares. And oh, I should probably mark that for us so you can see how that's spelled, because this is actually important. Antares. So the last part of that word, Ares or Ares, that was the Greek name for the god Mars. Mars was the Roman name. So this name, Antares, actually means rival to Ares or rival to Mars, because this star is so red that many people, both in ancient times and today, mistake it for Mars, the red planet. But it is indeed a star, and we're going to talk about its color a little bit more later. Antares is pretty easy to find in the sky because of its brightness and color, and also because it is part of a very easy to find constellation. So follow my cursor, and we're going to find this constellation. This is one of my favorites because I think that this constellation really does look like its name. So follow my cursor along this curving path of stars right here. This is the constellation Scorpius, and this path of stars is thought to look like the body and stinging tail of the scorpion. And then these over here are the scorpion claws. Just a little tip on observing Scorpius. You might notice that it's pretty close to the horizon, so it might be a little bit tough for you to see if there are buildings and trees in the way. If you happen to travel farther south in the summer, you'll get a better view of it because it will be higher up in the sky. And you don't have to go too far. I've seen some really nice views of it from Florida, Arizona, Southern California, not even that far south. Okay, so why is this star red? Well, we know that stars' color is based on their temperature. And it might surprise you to learn that the red colored stars like this one are actually the coldest stars. They're not cold. They're actually pretty hot because they're stars. But for a star, they're the coolest ones. And blue colored stars are the hottest and brightest. So looking around at all the stars, if we're trying to get information about stars to try to understand them and how they work, there's a lot of stars and there's a lot of information here. Color is one of the most obvious pieces of information, but there are others. So when you have a lot of information, you need a way to organize it. And one of the ways that scientists use to organize information is a graph. So has anyone ever made a graph of something in school? There's lots of different types of graphs, but they're a great way of organizing information. So I'm going to show you a graph that has a bunch of stars on it with lots of information about those stars. And this graph has a special name. It's called the Hertzsprung-Russell Diagram because that's the name of the scientists who first organized the information this way. So you see that on the bottom here, we have color, a beautiful rainbow of color. And I just explained to everyone that the color has to do with the temperature. So over here in the red is the lowest temperature, and over here towards blue is the highest temperature. Now on the other side here, we have something called luminosity, which means how bright it is. And this luminosity is based on the brightness of the sun. So a luminosity of 1 means the star has the same brightness as the sun. Going up, these have higher luminosity, and then these ones have lower luminosity. So these scientists took this information about stars and organized it in a graph, and they saw this pattern occur. So what was interesting was that Hertzsprung and Russell noticed that most of the red stars were less bright than the sun. You see how they have very low luminosity over here. But then there were a few red stars that were much, much brighter. And so Antares, the star we just looked at, is right about here on the HR diagram. The reason these stars are so bright, and you probably guessed it, is because they are really, really large. So a large object is putting out a lot of light. Now, Hertzsprung and Russell, I'm sure they asked themselves, why do most of the stars follow this nice pattern where the red stars are dimmer and the blue stars are brighter, but then some of them don't? Well, eventually we realized, not just right away, many scientists contributed, that we determined these stars, the ones that are in separate groups over here, are at different stages of their life than the main sequence of stars. All stars spend most of their life as a main sequence star. But then, as they get towards the end of their life, they begin to change. And for some stars, what happens is they get bigger. So they get bigger and therefore brighter, but they also get cooler. So they end up over here, cool, but big and bright. And this is what happened to Antares. Antares, we imagine, used to be a blue star, a big blue star over here, and now it is one of these red supergiant stars. So this is a very fascinating diagram, and it's a very, very useful tool for astronomy in so many ways. I really encourage you, if you have questions, to put them in the Q&A. You definitely don't have to do it now. You can wait till the end. But there are definitely so many things we can talk about about stars just looking at this diagram here. But remember, everyone, the star Antares was right about here. Okay. So now we're going to take a look at some other stars. So we're going to turn and face east. And now let's check out another pattern of stars in the sky that is very easy to find in the summer. So if you look up in the sky in summer, you might have your eyes drawn to three very bright stars. They're called Altair, Deneb, and Vega, and together they form what's known as the summer triangle. The summer triangle is not one of the 88 official constellations, but each one of these three stars are part of their own constellation. So let's take a closer look at Deneb. Deneb is a part of Cygnus. Cygnus is sometimes called the Northern Cross. So when you're looking for it, look for this cross shape, or like the lowercase t, you might say. But those of you that know your Latin, you will know that Cygnus means the swan, not the cross. So there is our lovely swan. And I would like us all tonight, we're not going to talk about the star Deneb. I'd like us to take a look at the star Albireo, which is right at the tip of the beak of that swan. So there's Albireo. This is a very popular star. It's a very popular target for small telescopes. I've heard some talk of using binoculars too, but I'm not as sure about that. But even very small telescopes, Albireo makes a great target. And let's take a closer look and find out why. So ready, everyone? We're going to get a closer look at Albireo. Oh, we need to get closer than that. It still doesn't look very interesting, does it? So we need to get a closer look. Okay, now it's starting to look a little bit interesting. Okay, so we can now see why this is such a popular target for amateur astronomers. What appeared as one single star is actually two stars, and this one is known as a double star. You may have heard the term binary star. We actually don't know if this pair is a binary system, meaning that they're gravitationally bound to each other. So binary stars are bound by gravity and they orbit around a common center of mass. We don't know if that's the case for these two stars, so we just refer to them as a double star system, meaning it's two stars that appear close to each other. But what's really interesting and beautiful about this pair is they both have very different, distinct colors. So Albireo A is an orange-colored giant star. It's about 60 times larger than the sun. Albireo B over here is a blue star on the main sequence, but it's not one of the really big blue stars. It's only about 3 times the star of the sun, 3 times the size of the sun. So we have two very distinct colors. The really interesting thing about this system, though, is that both Albireo A and Albireo B are actually themselves binary stars. So each one of these two stars, A and B, has a small binary companion, but those small companions are too small to be seen, at least in this view and with most telescopes. So you're actually looking at least 4 stars in this system, but there could possibly be more. All right, we're going to zoom back out. And I just wanted to comment on the fact that binary stars are very common. In fact, the star that we looked at earlier today, which I think we can still see, Antares, is also a binary star itself. But the two stars are too close together to make them out the pair with most telescopes. And the companion star is lost in the brightness of the primary star. Antares A, the primary star of this system, is huge. Remember we said it was a red supergiant? It is over 600 times larger than the sun. Its companion, Antares B, is 5 times the size of the sun. So pretty big, but nothing compared to Antares A. So it's lost in its brightness. Now, looking back on our discussion tonight, we've really only looked at 2 stars, Antares and Albireo. But we really got a sense of the variety of colors that stars come in. And we were also introduced to 2 of the most important tools used by astronomers to learn about stars, the HR diagram and binary star systems. We didn't have time to get into it today, but binary star systems are an incredibly important source for information about the structure and behavior of stars. So remember that list of things we looked at the beginning? What are all the different things we can learn about stars? First, there are some things that you can only learn about a star if it's in a binary system. And those examples have led to a huge amount of information that we have about all stars. Luckily for us, though, over 50% of stars in the Milky Way are known to be in binary systems or multiple star systems. So there's a lot of information encoded in this light here, but you all can start at home looking up at the real night sky by just looking up at the stars and trying to see how many different colors you observe. All right, well, that is my presentation for today. Those of you who are on Zoom, I want you to now think about what questions you might have that came up during the presentation and enter them in the Q&A window. I will be getting to your questions in just a moment, but I want to give you all a moment to think about questions. And while we're doing that, I'm going to take you all on a little tour of our website. It was brought up earlier, but I want to take a moment to really show you all what's there. So the main website for the Krista McAuliffe Center, which is the home of the Framingham State University Planetarium, is cmcenter.org. It's really easy to remember. And on our website right now, we've put everything that is most useful to all of you right here on our front page. So these are all resources that are going to be really useful to people who are learning at home. And just because it's summer vacation, we don't need to stop learning at home. Everything that is presented by the FSU Planetarium is here under From the Dome to Your Home. So if you click on that, you'll be brought to this page. This is the one that John showed at the beginning. This is the Dome to Home page. Now, on most of our pages, you will find a link that will give you a really quick and easy way to find out how to donate to support our programs. And I do hope that some of you will consider that. But anyway, I want you all to check out everything we've got on our page here. If you click on AstroNights, you'll see that every AstroNights event, including this one, has its own event page. So you can see some of the upcoming events. Those of you that are having a good time and want to come back again soon, we're having a very different but fun event next Tuesday. So just a few days from now, because Tuesday is International Asteroid Day. It's a day that is devoted to education and awareness about asteroids. And we have a couple of things lined up that you can check out now and sign up for. There's a couple of live virtual events. But if you click on tonight's event page, this is where you will find later, you'll find how to, you can send people here to see the recording and where I've put some resources related to tonight's program. All right, so with that, I am going to turn it over to the questions because we've got some good questions coming up. So let's go back to the lovely night sky. And I have a feeling we're probably going to take a look at the HR diagram again. All right. So the first question, it's something from the HR diagram that I'm not surprised came up. The question was, what are white dwarfs? Very good question, a fun word, a fun name, and I think we all probably want to know. So remember, I was explaining that at first, the HR diagram seems like a very simple way to classify stars based on information. You have the temperature here, and you have the brightness here. But one thing that's really important to know is that those characteristics for a star are not necessarily going to always stay the same. So when a star is born, it will end up somewhere on the main sequence. So when a star is born, maybe it's born small and red, or maybe it's born big and blue, but it's not going to necessarily stay on that place. So I mentioned that stars that are big and blue are eventually going to become supergiant stars. Slightly smaller stars are going to become giant stars. So, these ones here, this definitely could happen to the sun. The sun could end up on this path. It's not totally clear. But then there are other stages to the process. So what happens with giants and supergiants is basically the star expands. So its outer gas layers expand outward. And this goes on for a while. There's a lot of changes. It kind of contracts and expands for a long time. And then eventually, the star's core is going to run out of material. It's going to run out of fuel that it uses to make light. And when that happens, eventually the core is going to collapse in on itself. And this is a very, very violent event that creates a massive, for really big stars, it creates a massive explosion called a supernova. And that, violent explosion blows all of the outer layers out into space. Now, sometimes, depending on the star's mass, that the core gets left behind. So we have the outer layers getting blown off, but the core gets left behind. And that's what a white dwarf is. It's the leftover core of a star after it's died. So if you think about a star kind of in this part of the main sequence, it has sort of a path that it travels. It's going to become a giant, And then, so these stars don't actually have the supernova happen. They have kind of a lesser event, but it's the same process. The outer layers go outwards and a core is left behind and it becomes a white dwarf. So a star can start in the main sequence, become a giant, and then end up as a white dwarf. So that was kind of a long answer because it is a complicated question. But like I said, there's just so much to unpack here. And I will just make one more comment that white dwarfs, you can see they are very, very dim. They have very low luminosity. So you can't really see any of those in the sky or even with a typical telescope. All right, great question. The next question I'm going to go to is, how can you tell the difference between one star and another? It seems like there are too many to see, and so many seem alike. Such a great question. Yeah, I picked out a couple of examples today, like Antares and Albireo, where the color is really obvious. So that's one example where you can see the difference. But for most of the stars, you're not going to be able to see the difference with the naked eye, and you're not even really going to be able to see it with a telescope. But there are a couple of tools that astronomers can use to help them figure out some of the properties of stars. One of the really simple things that they can do is they can use filters. So if you put a red filter on your telescope, that's going to only allow red light to pass through. And then if you put a green filter on your telescope, that will only allow green light to pass through. So you can do both. You can do the red filter and measure how much light came through that filter. And you can do the green filter and measure how much light came through that filter. And if one of them is more, then that's what color the star is. So even though the star looks white, if you do a quantitative process, you can actually find out that it's emitting more green light. So technically it's a green star. So that's a really simple process that I think most people can understand, using filters to determine what color the star is putting out the most light. And our eyes are not really able to do that as well. There's another tool that's really important, which is called a spectrum or spectroscopy. So instead of just taking a picture of a star or just looking at it, you can pass its light through, it's called a diffraction grating, but the way you can think about it is think about passing the light through a filter. It creates a spectrum. So you're not looking at just the star itself, you're passing its light through a prism, and you see, and that's actually how you see that it's showing you all the different colors of light, that all the different colors, red, green, yellow, blue, are all part of the star's light. But it's going to put out a little bit more in one of the colors or more. But there's more in the spectrum than just the continuum of colors. There's more than just the rainbow. There's actually information hidden in there about things like what the star is made out of or how fast it's moving. So spectroscopy is a really, really important way of classifying stars. And there are other things you can do with stars' light to learn about them. These are all tools of astronomy, and I really do encourage you all to learn more. There are not a ton of resources up on the event page right now, but I will be adding more. Okay, some great questions. Let's see. Skipping around. Okay, there is a question. Oh, thank you so much for asking this question that I was supposed to ask myself, but I forgot. So the question is the sun red? And I actually want everybody at home to answer that question. So we still have the HR diagram up on screen. So I want you to look at the HR diagram and I want you to ask yourself, based on this diagram, what color do we think the sun is? Everybody think about that for a second. I actually do have this as a poll and I just forgot to give it. Oh, wait, oops. Yeah, I forgot to give the poll. But there it is. People should be able to see the poll. According to the Hertzsprung-Russell diagram, what is the sun's color? So those of you on Zoom, if you want to try answering that. But everybody should be asking each other. Oh, and then there's a second question. All right, I'm going to stop us right now, but let's see. I'm getting a lot of different colors. People are not all guessing the same color. I will tell you all the answer. The answer is that the sun is basically yellow. And here's the secret to finding that out from the diagram. So remember that over here on the y-axis, as we say, the luminosity is based on the luminosity of the sun. So these ones above on the top have a luminosity higher than the sun. These ones below have a luminosity lower than the sun. And a luminosity of 1 means the same luminosity as the sun. So obviously this is what the sun's luminosity is going to be. And if we follow this over, we see that this is kind of right in the yellow part of the main sequence. But I guess now that I think about it, we don't technically, you wouldn't necessarily know that. No, I don't know. I don't know. To me, it makes sense. But yeah, so at this luminosity, this is what the color of the stars are. So the sun is yellow. But I really appreciate you asking that, and I'm really interested in the poll results. That may not have been the most obvious, and I will have to think about that. But yeah, this is the sun. It's yellow, but someday it will expand and end up more red, at least more red than it is now. Okay. Other questions. Okay, this is the last one I'm gonna, well, actually, if you ask more questions now, I might take them, but for what I have now, this is the last one I'm going to take, which is, do all supernovas result in black holes? Okay, so black holes are something that obviously are not a part of the HR diagram. And think about why that's true. Because the HR diagram is all about light. It's because that's the only thing we can measure. We can measure how bright the star is. So that's how much light it is. And we can measure the color of that light. So those are really the two simple pieces of information we can get about stars. Now, something that does not produce light, then we really can't get much information about it. But we can definitely try, and we certainly do. So I mentioned that the very biggest stars, so these stars up here, the very, very big blue ones, those ones are the ones that become supergiants, and they end in these really big, violent explosions called supernovas. The question, do all supernovas result in black holes? I have to say, I'm not 100% confident in this answer, but I would say that the answer is no. Yes, actually, I am confident in that answer. The answer is no. Not all supernovas result in black holes. So basically, what's left behind is the core that gets really, really compressed. So it's a bunch of material that gets compressed into a small area. And when that happens, really interesting things can occur. So if you compress the matter down really, really far, it becomes something called a neutron star. And then for, we think, the largest stars, the very largest ones, if you just continue compressing that matter farther and farther, and like there needs to be a lot of matter for that to happen, then that's when the object can eventually become a black hole. It's basically a huge amount of matter compressed into a really small area. And because of that, the gravity of that object, the gravitational force, is so strong that nothing can escape from it, including light. And that's the definition of a black hole. All right, so I hope that if you're interested in black holes, you will come and join us again in the future, because I believe we may have some programming on that in the future. All right, so with that, I am going to end our presentation at this time, but I do want to remind everyone to check out our website. We do have some resources up there and information about upcoming events. We have the opportunity to donate on our website. And I also just want to end by saying, please, everyone, take a moment this summer to head outside and take a look at the real sky. And finally, those of you who are still with us on Zoom, when your Zoom window closes, you should be given the opportunity in a browser window. There'll be a link for you to complete a survey, and we would really appreciate it if you would do that. So thank you so much, and everybody have a lovely evening. We hope to see you again at a future AstroNights event.